Let's check this new paper. The first author sent it in my Discord. It tries to solve the quadratic scaling of the attention. My Discord and the paper URLs below the video. So it's from Carnegie Mellon University. If you worked with transformers, you know their power. You also know their kryptonite, the dreaded O(n) squared complexity of the self-attention mechanism. While this is manageable for text sequences of few thousand tokens, it becomes a computational nightmare when n scales to hundreds of thousands or even millions, as is common in scientific simulations on large meshes or point clouds. Or if we have millions of text tokens, so this idea can be applied to that situation as well. The paper FLARE, Fast Low-Rank Attention Routing Engine, introduces a clever and highly effective solution to this problem. Let's break down how it works step by step. The core problem, why standard attention fails at scale. So you see the scores, query times key matrix, we all know this, so I will skip this. But you see it's quadratic scaling. The longer this Q, the longer the K. So for each token has its own Q and K. Sometimes it's a bit grouped, so a bit maybe less of the keys. But anyways, it always has this quadratic scaling. So for 1,000,000 tokens, this matrix would have 1,000,000,000,000 entries. That would be almost infeasible or infeasible to compute and store. To have 1,000,000,000 of those results where each key multiplies each query. Key insight. Attention is often low rank. The authors of FLARE, like others before them, built on a key observation. The massive n times n attention matrix is often low rank. In simple terms, this means the complex all-to-all communication pattern can be approximated without every token talking directly to every other token. Instead, the information can be routed through a much smaller, intermediate set of hub tokens. It makes sense. When I'm reading a book, I don't actually need, not every word has some correlation with every other word. Just certain words have correlations with some other certain words or sentences, but it's not that every correlates to every other. Imagine a city of n people. Standard attention, every person calls every other person directly, so n squared phone grid. Low rank idea, everyone routes their calls through a central switchboard with just m operators, where m is much smaller than n. FLARE builds a learnable version of this central switchboard. FLARE introduces a fixed size sequence of m learnable latent tokens. These tokens don't come from the input data, they are model parameters, just like the weights in a linear layer. Let's say our input x has n tokens, example n points on a mesh, and our latent sequence has m tokens, let's say m is 128. So input sequence n tokens can be millions, while latent sequence m is a fixed small number, 128. The entire FLARE mechanism is a two-step dance of routing information from the n tokens to the m tokens and then back again. FLARE replaces the single self-attention step with two sequential cross-attention steps. So instead of single self-attention, we have two sequential cross-attentions. Part A. Encoding input to latent. The first step is to compress or summarize the information from the n input tokens into the m latent tokens. First, get keys and values. Just like in standard transformer, we create key and value matrices from our input x. These have the shape nd. So d is like dimension, I guess, of each key and value, while n is just the number of tokens. So this is a matrix, one of them for keys, one of them for values. Use latent queries. Here's the magic. Instead of creating a query matrix from the input, we use our learnable latent sequence as the queries, okay? Instead of creating a query matrix from the input, we use our learnable latent sequence, our m sequence, as the queries. Let's call this Q latent with shape MD. And so now we do the cross attention between the latent queries and the input keys values. So we just do Q latent at keys transposed. And then we just use that result for the multiplication with values. The result Z is our compressed latent representation. We've effectively summarized the entire N token sequence into just M tokens. This operation has a complexity of O of N times M, which is linear in N, which is basically because M is a lot smaller and it's consistent. So I guess the way they calculate these complexities is you can just ignore M in this case because it's very small and constant. Then we have decoding that goes from latent to input size again. Now we need to distribute the summarized information from the M latent tokens back to each of the N original tokens. Swap roles. We cleverly reuse the same components. The original input keys now act as the queries. The latent queries, Q latents, now act as the keys. Now I think they just swap. Now use latent values. The compressed repetition Z we just calculated now serve as the values. So these are the latent values that we calculated. Perform a second cross attention. So here queries, which is in our case the keys. A bit confusing here, but just swap keys and queries and then do this. The final output Y has same shape as the input ND, but each token has now received global information that was routed through the latent bottleneck. The second step also has complexity of O of N times M. Looks like you can just use scale.product attention from PyTorch because this is very good. If you can just use this, it's very optimized, very fast. So this is a cool paper, it's a cool idea. I'm gonna end the video here. For those of you who want to learn more about this, who want to dive deeper into this or use this in your research, I'm gonna leave the link below. The first author is on my Discord, and on this Discord we do like research, we talk about AI. So I'm gonna leave the link below. Also check other videos on my channel and see you next time.